Okay, so it's really nice to see that Stephen is able to be much more active than he was a few years ago. And so I'm talking about really calculations that were done over 20 years ago. So why should we, is it worthwhile revisiting? Well, so what I'm talking about in this here in the context is very large Schwarzschild black holes, mass very large compared to the Planck mass, which are formed by spherical collapse in that partly flat space-time. And where the initial, before the formation of the black hole, long before the formation of the black hole, you can think of just as having essentially a Minkowski space-time, and then the star collapses from some large distance and forms the black hole. So that leads to the formation of a apparent horizon at r equals 2m, trapped surfaces inside the outer boundary of trapped surfaces, and that persists for many dynamical times. Now, in other words, this is not taking the point of view of Bohrstock, obviously. Now, whether or not there's an event horizon is an open question, and really I don't think very important for understanding the properties of the black hole. Okay, now, on this classical background, we have quantum fluctuations, which can be considered, test fields on the classical background. And this is the semi-classical approximation. Now, so the quantum corrections should typically be of order the ratio of the square of the Planck mass to the mass of the black hole. And that's 10 to the minus 76 for m larger than one, less than 10 to the minus 76 for m larger than one solar mass. So for any black holes we know about in the universe, this is the semi-classical approximation should be about as accurate as any approximation ever is in physics. Now, but it definitely breaks down in the deep interior of the black hole, especially small r, and it may eventually break down at the horizon, the outer horizon, as long as the black hole, after some very long time, as the black hole evaporates. Certainly, if the black hole evaporates down to the Planck mass, it breaks down. And I'm not going to set h bar equal 1 here. I'm going to. So, okay, so why do this? Well, we're talk about this now. Well, partly is that a lot of, I think, things that were well understood at the time, during the 70s and 80s, have, in terms of physical interpretation, have gotten somewhat lost in the depths of history and need reemphasizing. The other is that a lot of the results on the energy momentum tensor around these black holes, the expectation value of the quantum energy momentum tensor, are results which were never, well, numerical results, result of rather lengthy, complicated calculations. And the published results are in the form of graphs, and often not very well designed graphs. So it's very hard to extract accurate information from those graphs. And so I've done the best I can to do that and make numerical fits to the numerical results in terms of analytic expressions, as I'll explain. Now, another issue I think that needs perhaps reinterpretation is the role of the conformal anomaly in the energy momentum tensor, I'll talk about, and also debunk what I consider myths about where the Hawking radiation is created. In other words, I can argue that it's not created very close to the event horizon. It's really created at the potential barrier, which is around R equals 3m, and that all that happens at the event horizon is that negative energy is flowing in, but there's no pair creation occurring at the event horizon in some small region. And in particular, models which try to calculate the Hawking radiation by assuming some sort of tunneling over a Planck distance around the horizon, I think are just wrong. Now, another thing I'm going to argue, though this is not the main subject of the talk, is that quantum information will not be stored, cannot be stored for any length of time outside the black hole, and that the quantum information is associated with the outgoing Hawking radiation ends up inside the black hole, and so that means there's no simple resolution to the Hawking information paradox. Okay, so okay. Now, what can we say about this semi-classical energy minimum tensor? Well, so what we have results for, our numerical results are for spin 0 and spin 1 fields, on the Schwarzschild background, and of course some other cases as well, but these are most interest certainly for black holes we know exist. And unfortunately, there are no calculations for gravitational quantum, gravitational perturbations of black holes, so that's still open. Now, by assuming spherical symmetry, we reduce the energy of tensor to just 4 independent components: the energy density, energy flux, radial stress, and transverse stress. And these are related by, are constrained by conservation equations, zero covariant divergence, and by the fact that I'm going to, assuming that, as is normal in the case of Hawking radiation, that we're talking about is radiation that's produced long after the star has collapsed. I don't believe that the collapsing star itself, while it certainly produces some pair creation, some radiation, that is not what is conventionally meant by Hawking radiation, and that that is just a small amount of energy release initially, but then steady Hawking radiation that continues on. It has nothing to do with the collapsing star. And so what do you expect the fields around the black hole to relax to some sort of stationary state in not a static state, but a stationary state over a few dynamical times. For instance, the normal modes of black hole decay exponentially with time scales of the order of m, and therefore we can assume that the quantum measurement tensor is going to be time independent, which means then we reduce the energy conservation to just divergence of an energy flux there, and the momentum conservation relating the radial stresses and gravitational acceleration. Now, an important issue here is that, so the fields I'm considering, normally coupled spin 0 and spin 1 fields, if one makes the normal assumption, then for these classically conformally invariant fields, the only contribution that you get a non-zero trace to the intervention tensor from renormalization of the fields. In other words, the quantum theory is not conformally invariant. But given by a trace for which we have an explicit expression in terms of the background curvature tensor, where it's split up into a vowel tensor and Ricci tensor and Riemann scalar. It has this form. And for a social black hole, it just goes as n squared over r to the sixth. With a coefficient q, which depends on spin, it's 1 for scalar, the way we define things, minus 13 for electromagnetic, and for spin 2, in other words, gravitons, it's 212. So there's a strong increase in the magnitude of the formal anomaly with spin. Okay. Now, of course, to talk about the energy intensity, we have to specify a quantum state. Now, the two commonly discussed states are Hartle-Hawking and the Unruh vacuums. Now, I want to say that the way I view this, it is just a choice of quantum state. It's not really a choice of vacuum. A choice of vacuum depends on what observers you have, where they are, and so on. So this energy momentum tensor, this semi-classical energy momentum tensor, is not something that would be measured by any particular observer in any particular place. It's what this describes essentially the first order back. It's the source for the first order back reaction of the quantum fields on the geometry. So it's important for that reason. But it's not something that's observer dependent. And now, if you want to interpret this stress quantum fields in terms of particles, of course, that is observer dependent. Depends on the choice of what you consider the vacuum. But here we're not going to be doing that so much. For the Hawking radiation, when one goes out to some very large radius where space-time is approximately flat, and there the natural choice of vacuum is the Minkowski vacuum in the asymptotically flat region of space-time. So that gives an ambiguous, at those very large distances, gives a sense of what you mean by the Hawking quantums that are coming out. But near the black hole, there isn't any obvious particular choice of observer that would have any particular preference for others. Okay, so the Hartle-Hawking vacuum is a thermal state, which is no energy flux anywhere in the static frame of a static observer outside the black hole. And at large R, it approaches an isotropic, it approaches an isotropic gas of radiation, and as for essentially large R, it's essentially radiation in the equilibrium. So you think of it as a thermal gas in equilibrium in the gravitational field, which you can solve without, and it's just pressure going is 1 over 1 minus x, where x is 2 over r squared, and then you can expand that as a power series. And so for the first few terms in this power series, we expect this to hold, but there'll be corrections at higher orders. And this pressure infinity is the pressure of a thermal gas, which is 2/3 sigma TDH to the fourth for Hawking temperature pH, and it's times the number of Felicity states per mode, which is 1 for scalar, 2 for photons. Now, so for my purposes, I'm interested in black holes that really exist in the universe, which are not in thermal equilibrium with the gas, with radiation. And but still, we have to discuss the Hartle-Hawking vacuum, because the way so I really want to consider the Unruh vacuum, but the Unruh vacuum, the way the calculations were done for the Unruh vacuum was first do them in the Hartle-Hawking vacuum, which is somewhat simpler, and then calculate the difference of the energy tensor between the Unruh and the Hartle-Hawking vacuum, which calculating the difference is a lot easier than calculating the Unruh vacuum itself. So That's the way the calculations are done, the way the results are presented, so we have to consider both. So now, the under vacuum then is the state which corresponds to Minkowski vacuum in the distant past before the black hole formed. All right, and so we just extrapolate that on, and there's no incoming radiation at past no infinity, and we assume that it's a regular and a freely falling frame at the future horizon. And there's an outgoing flux of radiation, Hawking radiation at the luminosity, which again can be written in terms of this sigma th in the fourth, with a coefficient which depends on, again, a calculation of mirror penetration factors and so on for all the different modes. But Page has calculated that early on and got these values. So this is something which decreases with increasing scan. And at large R, we expect the energy tensor to be that of just radially propagating radiation, where the transverse stress is small compared to the energy density, and the energy density and radial stress and energy flux are approximately equal. Now so this is something that applies once the transient effects that are associated with the actual formation of the black hole have dissipated and we've approached a stationary state. And okay, now, before actually talking about the numerical results, I want it's important, I think, to look at how this total energy movement tensor is composed of different components. Now, where I differ from some of the earlier work is in how I do this. Now, in particular, for the conformal anomaly, so conformal anomaly gives a trace to the energy tensor but itself, doesn't tell you much more, but one can make the following argument that, okay, the conformal anomaly, the trace just depends on the geometry of the background. It doesn't depend on the quantum state. And therefore, there should be a component of the energy movement tensor which also depends only on the curvature of the background, not on the quantum state. And that component must be conserved separately from the rest of the energy movement tensor, which does depend on the quantum state. Because obviously, you can't have, I think it's obvious that you can't think of something that's fixed independent of the quantum state as being coupled to the quantum state dynamically, to the part that is dependent on the quantum state dynamically. Now, if it also says that because the background curvature for Schwarzschild is independent of, is invariant under radial boost, that should also be true for the energy momentum tensor associated with the background curvature. And then that tells you that, essentially, that you have this relationship between the different components. There's no energy flux in this component, and radial stress equal minus the energy density, and the energy density is half of the trace, and the transverse stress is equal to the trace. So all those are given in terms of then in terms of this, explicitly in terms of this quantity as a function of radius. And now in analytic sessions, analytic attempts to derive analytic formulas for the energy tensor, for instance, at a Page, there's usually a component separated out which has a non-zero trace, while everything else is traceless. But for instance, in the case of Page, that component has no transverse stress, just energy density, negative energy density, and positive radial stress. And but this is not conserved under momentum conservation. So now the other issue it has to deal with is that for the unroot vacuum, there is a non-zero energy flux, and the conservation equation showed in the last slide demands that in a static frame that the energy flux be infinite on the horizon. That's because there's an infinite redshift, right? There's a steady flow of energy outward, but, well, not flow of energy, but there's a conserved energy flux, which, because there's an infinite redshift from the horizon to infinity, implies an infinite, as measured in a local static frame, an infinite energy density. Of course, the reason for that is that the static frame is moving at the speed of light relative to any freely falling frame at the horizon. So when you take an instrument tensor and boost it to, v equal 1, you're going to get a singular energy momentum tensor typically, unless the energy momentum tensor has very special properties, like for instance the Sitter instrument tensor. So since I want to talk about non-singular quantities as much as possible, I'm going to separate out a part of the instrument tensor, which is, again, which is conserved, and which contains all of the singularities associated with that infinite energy flux in the static frame on the horizon. So this is, again, all in a static frame I'm talking about. And so, so you have there's no transverse stress for this component, and you have this corresponds to an ingoing flux of negative energy, because the sign of the energy density and the pressure is opposite to that of the energy flux. You have a positive energy flux, so you have negative energy density and pressure, radial stress. Now everything else I call the regular part, and because the conformal anomaly contains the trace, this has zero trace, and we can, because this is regular everywhere, we can hope to represent it as a polynomial in X, and find the coefficients, and use that to derive a analytic expression. Okay, so now, so energy conservation is just what tells us what the radial dependence of the flux is, energy flux is. Momentum conservation gives relations between the coefficients and radial stress and transverse stress. And I won't discuss this in detail, except that, this is basically assuming we're going to evaluate the transverse stress and try to calculate the radial stress. But notice there are some constraints on the transverse stress you have to take into account, like this one, and because we want these coefficients to be coefficients of a polynomial and not an infinite series, we have to terminate them at some maximum order polynomial of order capital N, and that requires that the coefficients for the next n capital N plus 1 for both the transverse and radial stress be 0, and that gives us then a relationship which determines the maximum order, and this is for n equal 8, just for example here, in terms of the lower order coefficients. And then one thing I want to point out is that once you satisfy these conditions, then you can show that for the regular part, the radial stress is minus the energy density exactly at the horizon. And in literature, sometimes this is discussed as if it were some extra regularity condition, but in fact, it's not. It's just applied by momentum conservation. So we have, of course, assumed that things are finite by using polynomial representation. Okay. Now, there are certain asymptotic, depending on the assumption, one state we assume, there are asymptotic conditions. As I said, for the Hawking radiation, it's that the pressure be isotropic for at least the first few orders in expansion powers of 2 over r. And now where we expect the possible deviation in this is at n equal 3, because geodesic deviation due to the structural curvature of the structural background causes acting on trajectories which are non-radial, causes them to alters their behavior from what it would just be in a say, uniformly accelerating frame of class space, and has the potential of generating pressure anisotropy. And we'll see that in our numerical fits that we often do have to include n equal, allow things to deviate from this terminal expansion at n equal at 3 or greater. In contrast, there were some of the attempts to construct analytic fitting formulas that tried to assume a strong thermal hypothesis, which is that the first order, that the deviation from isotropy at first occurs happens at order x to the 6th, corresponding to the square of the curvature, but I don't see any really good physical motivation for that assumption. And no, that's for the Hartle-Hawking vacuum. Now for the Unruh vacuum, again, so we have outward radial flow at large r, and that implies that for the radial stress, we have that the expanding 1 over 1 minus x in powers of x tells us that, I'm sorry, expanding taking into account the redshift, just the redshift, but assuming purely radially propagating radiation, that the R sub n should be uniform, and for purely radially propagating radiation, transfer stress is 0. And so for n less than 4, fourth order in the expansion, I'm saying that things should behave as radial stress, behave as a radially propagating fluid. Now, we expect deviations at order x to the 4th, both because the radiation is not really going out radially. If you think of it as an observer looking at arc duration, it should see the radiation is coming from something like the black hole shadow. So it has a distribution of directions. And if you take that into account, that produces a correction in the momentum tensor at order x to the 4th. And also we expect deviations due to quantum vacuum polarization effects and those things which are not classical interpretation. So what are the results? Well, of course, there were analytic derivations of analytic approximations in literature, most notably for spin 0, Hartle-Hawking, page 1981 gave this expression for the transverse stress. And once you give the coefficients for the transverse stress, you can find everything else. For spin 1, Hartle-Hawking, there's an analytic formula given by Jensen and Ottewell. And for the Unruh vacuum, I'm not sure how to pronounce it, gave analytic approximations. Then there are numerical results, and in particular for spin 0, Hartle-Hawking, Howard, and then Anderson et al. Fortunately, these numerical results are given in a table in a paper by Visser, where he constructed an analytic that would be Unruh vacuum. For spin 1, Hartle-Hawking, Jensen, and Ottewell just have graphical results. And for spin 0 and spin 1 difference, there's a Jensen, McLaughlin, and Ottewell paper, which gives results, again, in graphical form. Now, for spin 0, Visser includes both spin zero Hartle-Hawking and spin zero Unruh table results, so and he did a fit for Unruh, and it makes it easy to do a fit as well. But for the spin one cases, one just has to rely on graphs, which, as you'll see, has some problems. Anyway, so polynomial fits for spin zero Hartle-Hawking, making this so-called strong thermal hypothesis, and you got a reasonable fitting at n equal 8 rather than n equal 6. And I found if you don't make the strong thermal hypothesis, you get an even better fit with n equals 6. And for spin zero Unruh, Visser did a numerical fit, n equals 6. And for spin one Hartle-Hawking and the difference, I've done numerical fits. Of course, you know, both this and this you can find under both. My fits are, for that case, are n equal 8. So, okay, so this shows, let's see, okay, this is a figure from Jensen and Ottewell. So what they're plotting here, well, this delta theta theta is essentially the difference between their numerical result for the transverse stress and their analytic formula for the transverse stress. So now, what their actual results are this little curve at the bottom here. And because they wanted to compare with other people's analytic formulas to show how bad the other formulas were, it ended up meaning that their actual numerical results are valid, are really, it's very hard to get any sort of accurate numbers out of that graph. But I did the best I could. And things are better for the spin one. Sorry, for the difference between, this is spin one, the difference between the Unruh vacuum and the Hartle-Hawking vacuum. And this curve is for spin one. And so it's possible to get numbers here accurate within maybe 1 or 2%. On the previous case, it's more like several percent, roughly reversed. And so this is the spin zero result here for the difference. Okay. Okay, so fits. So these are just some of the formulas I came up with. Well, the second for the spin zero Unruh vacuum, it's just the fit of Visser. And so for the difference, so this is, here is the difference between this delta theta theta, or minus delta theta theta, which is the spin one analytic Hawking formula minus the numerical result. This is from Jensen and Ottewell. So that's where the graph is very hard to read accurately. And so these numbers, coefficients here are rather uncertain. But anyway, notice there is an x cubed term here, which has the wrong sign to correspond to the analytic formula because it means that we have to have an even larger if we want to say there's no x cubed term in the Unruh vacuum case, it means we're forced to have this large coefficient in the delta theta theta, and that implies large coefficients elsewhere. Given the poor quality of the data, I mean, if we didn't have this constraint that we want the T3 and for the Unruh vacuum to be 0, that then what you'd find just as good fits, much simpler fits, but But I think there are good physical reasons to say that we do not want an execute term for the unroot vacuum. So, and for the unroot vacuum then, we have this expression for the difference, and notice these large coefficients. That doesn't mean that the result is large. It means the Allerton sign largely cancel, but it's what is necessary to fit the curve. Okay, so this is now comparing the the Hawking spin zero case, where we have the page approximations, the green line, and then the black points are taken from a table in the Visser paper, and which is based on calculations of Anderson et al. and Jensen et al. And the red curve is the fit, which you can see is quite good. Okay, so now for the delta theta theta, for the spin 1 Hartle-Hawking vacuum, these points are probably not known to better than 10% of the, or several percent anyway, of the vacuum of the maximum value. And so particularly here, it's pretty uncertain. And with that caveat, you've got a reasonable fit. And then finally, for the spin 1 difference of unruh and Hartle-Hawking, here I'm showing the data points I've extracted from the graph and my numerical fit, and then this is the difference of the analytic findings. Okay, so now how to analyze this? Well, one thing, as I said, is I want to understand something about where the Hawking radiation is being generated. Is it being generated close to the horizon or further out? And one way to try to get at that is to look at this quantity, which I call F out. So this E combination E plus P radial plus 2 times the energy flux is something which is equal to 4F, because for a purely radial outflow of positive energy, the energy density and radial stress and energy flux are all equal. So this is 4F, and this divided by 4F gives something which is just 1. Now, if we have purely ingoing radiation, then the energy density and pressure split sign for the same energy flux, and so we get this vanishes. Now, so to the extent that it's reasonable to look for pure radial flows, then this tells you how much of the radial flow is outward positive energy, how much is inward negative energy. All right. Yeah. And this, here it turns out that the sum of the energy density and radial stress, the stress in terms of the radial stress and the transfer stress of the regular part of the integrand tensor. And we can write that, since we know that vanishes on the horizon, we can write that as 1 minus x times the function z, and then F infinity, this F infinity goes as 1 minus x squared times z. So it vanishes on the horizon. And of course, the reason for that is that well, so on the horizon, we can't really, in the static frame, we can't really have outgoing radiation. But we can have ingoing radiation. And the ingoing radiation in the static frame is infinitely redshifted. So F infinity has to vanish. Now it also vanishes because the flux goes to infinity at the horizon. Now, so that gives two factors of 1 minus x. Now, spin 0, it turns out this Z has this nice simple formula. For spin 1, things get messier. And so I would say this means that while this interpretation of this radial approximation makes some sense for spin 0, it doesn't make much sense for spin 1 in the vicinity of the horizon, of course, further out. Now, and so the idea then is that the net flow of Hawking radiation is small compared to the other contributions, the other contributions to the energy tensor, which do not cancel out. Now, if you have something in the energy tensor which has radial stress equal to minus the energy density, that doesn't contribute to this F out, but something more complicated does. So now, if F out is negative, it means the outward part of the energy flow has negative energy. Okay, so what are the results? Well, for spin 0, this is comparing the analytic and numerical results for spin 0. And you can see there's a nice smooth transition. Remember, X is 2 over R, so it's 0 at infinity, R at infinity, where you have purely outgoing radiation. And at the horizon, you have purely ingoing radiation. This is in the static frame. And the transition, where you go from mostly outgoing positive energy to mostly ingoing negative energy, occurs right around X equal 2/3, which is R equal 3m, which is where the peak of the potential barrier is. So I'm thinking this is a really good indication that you should think of the particle creation as taking place in the general vicinity of course, not right at, it's distributed over a range of radii, substantial range of radii, but around the peak of the potential barrier, which I think makes excellent physical sense. Now, as I said, for spin 1, things get, well, first notice now a very big discrepancy between the analytic expression, which is the green line, and the numerical expression, which is the red line. And the numerical expression is positive, corresponding to outgoing Hawking radiation dominating this part of the energy band tensor. Only for very small x, essentially, you have it, the outgoing fraction is positive only for R greater than about 12m, but closer to the black hole, you have it's becoming very negative, and which means that to the extent that any interpretation in terms of radial flow is possible, this corresponds to an outward flow of negative energy rather than, which certainly is not Hawking radiation. And then, of course, they have to go to 0 also on the horizon. So now we can also look at the energy band tensor in a freely falling frame, where there are no singularities now in the freely falling frame. And I just point out that you can, in terms of the quantities we define, you can write this in this way. So there's the ingoing negative energy part that we separated out have these involve this 1/1 plus square root of x, which is corresponds to the redshift of the ingoing energy in the freely falling frame relative to infinity, and then we have so this gives the energy density in the free fall frame, the energy flux in the free fall frame, and the transfer stress in the free fall frame. So notice that for x equal 1, the part that involves this quantity z, which is related to f out before, is this, everything does correspond to outgoing. So at x equal 1, the energy band tensor splits up into an outgoing, radially outgoing part, a radially ingoing part, and then a part which has, including the conformal anomaly, which has radial stress equal to minus the energy density and no energy flux. So, so in the freely falling frame, this is a frame freely falling from rest to infinity, there are typically finite non-zero amounts of both ingoing and outgoing radiation on the horizon. The ingoing radiation always has negative energy, but the energy of the outgoing radiation can have either sign, depending, as we saw, for the comparing this spin 0 and spin 1 cases. Okay, so in other words, if Z is the sign of Z, which is positive for spin 0 everywhere, and not negative anyway, and for spin 1, Z becomes negative around R.18 or something. Okay, so so my conclusions then are that, well, I think the semi-classical theory should be taken very seriously. There's no obvious reason why it can break down, as long as the black hole mass is large compared to the quantum mass. The Hawking radiation is, as I said, generated in the vicinity of the potential barrier around article 3M, not by tunneling across the horizon. So you have vacuum fluctuations, which get excited by essentially by the tidal effects of the geometry of the black hole in this region near the horizon, and part of them sort of leak out through the potential barrier and become Hawking radiation, and part just fall into the black hole. And particularly for larger spins, almost all of it goes into the black hole. There's nothing to indicate, well, that there's any sort of, anything hanging around just outside the horizon, any sort of contribution to the tensor, which is, this is maybe not completely obvious in what I've shown you, but anyway, I think the implications of the semi-classical approximation are that there is no storage of quantum information in the stretched horizon or in the zone, that everything ends up basically ends up in the black hole. All the entanglement with the Hawking radiation ends up inside the black hole, not outside. So now, of course, it takes more of a dynamical time over M to fall into the black hole, so it lasts at that time. But much longer requires that you would have some sort of propagating very close to the horizon, which means enormous energies in a freely falling frame, and after a time short compared to the evaporation time, infinitely even more energy than is in the collapsing star forming the black hole. So long-term Hawking radiation definitely has no source in the collapsing star. Everything, and as said, nothing is sort of left behind. Everything either goes off to infinity or to the black hole. And so the quantum information keeps accumulating. Of course, this means then we're faced with a Hawking information paradox, because if the black hole keeps evaporating down to down until the mass of the black hole is the order of the Planck mass, which is when the semi-classical approximation outside the black hole definitely breaks down, then you're faced with the problem that you have a huge entropy in a very small amount of mass, and there are reasons why that's uncomfortable, at least. Some people are impossible. But it does make me uncomfortable. So is there some way out of the information paradox? And this is don't have time to really talk much about this at all, but point out that general relativity is not conformally invariant. So perhaps there's an additional contribution to traces the Einstein tensor, which is not given by the conformal anomaly, associated with quantum gravity. And possibly it's much larger than the conformal anomaly. And I talk about these ideas in this Stockholm paper. Now, what I do is conduct sort of a toy model in which I assume that the effective energy momentum tensor inside the black hole is dominated by something which behaves like the conformal anomaly, which is the only part that we can extend into the interior of the black hole of any confidence. But so assuming that that has the same form, but just with a coefficient which can be much larger than or the Planck squared, which is what the semi-classical approximation says. And and this coefficient, I'm assuming, is proportional to the von Neumann entropy of the black hole. So arguing there's some effect of quantum gravity which is related to the amount of entanglement between the interior of the black hole and the exterior Hawking radiation, which generates a substantial back reaction over the whole range, which is not predominantly inside the black hole. But now as the von Neumann entropy approaches the Becker-Stein-Hawking entropy, and now if you take some sphere inside the black hole and say that all the infalling quantum information falls inside that sphere, then the number of the von Neumann entropy of the black hole essentially is equal to the von Neumann entropy inside that sphere inside the black hole. Now, if we believe in the Russo covariant entropy bound, which says that the entanglement entropy across the two-dimensional surface cannot exceed 1 per Planck area, then as we reach the page time, it requires an area for some inner apparent horizon to be equal to the radius of the outer horizon. Now that in that extrapolation, the back reaction, well, it's small as long as the entanglement entropy is small compared to the Becker-Stein-Hawking entropy. It gets to be of order 1. And at that point, any sort of semi-classical or even quasi-classical picture of the black hole is no longer valid. So it's pretty wild speculation. But the basic idea then is I'm assuming that the gravitational collapse does not lead to a singularity, but some chaotic core inside an inner apparent horizon, which, as suggested by Hawking, a paper a year and a half ago. And quantum information accumulates there. Then if you enforce the Russo covariant entropy bound, that area must increase, which means the radius has to increase. And then by the page time approaches the outer apparent horizon. So now at that point, if you end up with still a horizon, but a degenerate horizon, the quantum information stays trapped, but the degenerate horizon has 0 Hawking temperature, so the Hawking radiation turns off. And so if this picture is correct, then you end up with a massive remnant, mass about half the original mass of the black hole, which contains all of the quantum entanglement associated with Hawking radiation, and persists as a sort of a black object, a really black hole. And the other, it's also possible that instead of just sort of astronomically approaching each other, that the hydrogens actually disappear, so that there are no trapped surfaces anymore, and the trapped quantum information can escape completely, and that might involve some very energetic explosion, because while things are redshifted going along the outer horizon, they're blue shifted going, particles going along the inner horizon are blue shifted, as opposed to along the outer horizon being redshifted. So you have this sheet of enormous energy along the inner horizon, which, if it can escape, would end up producing perhaps some quite violent explosion. If you say this rapidly. Or it might just gradually leak out. But anyway, this is all speculation. Thank you.